Hello everyone, myself Professor Kishan GS, Assistant Professor, Department of Mechanical Engineering, Maharaj Institute of Technology, Mysore. In this session, we are going to study the subject Material Science 18ME34 for the third semester Mechanical Engineering students with the module 2. So the module 2 consists of two phases. One is failure of material, another one is concepts of formation of alloys. So in this session, we are going to start the first part of failure of materials. That is, we are going to deal with three different parameters here which defines the failure of material once the material is subjected to load. The first parameter being fracture, followed by fatigue, and the last one being creep. So these fracture, fatigue and creep are defined based on different parameters, like based on the nature of loading condition, based on the nature of material, type of strain which is being resultant as a part of application of load as such. So before starting with different failure of materials in a material, we are going to just rebrush about the material in elastic and plastic limit. So once a material is subject to a loading condition, upon unloading, if the material has the capacity to come back to its original shape and size, we are going to define the material in elastic limit. If the material cannot come back to its original position and original shape and size, upon unloading, then the material is considered to be in the plastic limit. So the failure of materials, whatever we discuss here, is always a consideration of material in the plastic limit itself, so that there will be a proper desegmentation of material into two or more parts. So the first of its kind is fracture. How do we define fracture? So fracture is defined as the separation of a solid body into two or more parts under the action of load. Upon the application of load, if the material breaks into two pieces, then we say the material has undergone fracture. Here in fracture, we have three different types. The first type of fracture is the type 1 fracture or the ductile fracture. So here what happens, before understanding something called as different types of fracture here, we are supposed to consider a material which is subjected to a type of loading condition. So whenever a material is subjected to loading condition, there will always be an initiation of deformation happening within the atomic bonds present in the material. So here that dislocation of atomic bond and resulting in the formation of new surfaces is always a resultant of fracture. Means to say that once a material is subjected to a loading condition, the material breaks and one material gets connected into two pieces. So this is how the fracture is defined, and this is how we are going to study different types of fracture. So the first one is type 1 fracture, that is ductile fracture. In ductile fracture, we have two types. One is highly ductile fracture. Another one is moderate or cup and cone fracture. So what do you mean by highly ductile and moderate cup and cone fracture? So here, before understanding these two, let us discuss what is mean by ductile fracture. So ductile fracture is defined as a slow crack propagation resulting in extensive plastic deformation before the material fails or before the material undergo fracture. Means to say that when the material is subjected to a loading condition, upon application of load, there will be a propagation of crack within the material, and that crack propagation will be very slow, such that at one particular point of time, it breaks the material into two pieces. So keeping this in context, we are going to study the first one, that is highly ductile fracture. So here what happens, consider this as a test specimen, and the cross section of test specimen is circular in its nature. Upon application of tensile loading condition, that is when the material is being loaded on the opposite direction outside, that leads to reduction in the cross section of material at one particular point. Here specifically in highly ductile fracture, when the reduction of area is exactly at a point, means to say that when this is a particular point of focus is taken, if the reduction in area is 100% at one particular point of time, that leads to the separation of material into two pieces, and that particular type of fracture where 100% reduction is seen at one particular point is called as highly ductile fracture. So you can observe in this figure here, so this represents continuity. So upon application of loading, there is one particular point wherein the 100% reduction in the cross area is seen. So wherein which the material gets separated into two pieces. and hence this is considered to be highly ductile fracture. Moving on with one of the major of its kind, cup and cone fracture or moderate ductile fracture. So here we are considering a material in its A condition, that is a standard test specimen, which is now being subjected to the load P on both the sides. Means to say that the test specimen is subjected to a tensile loading condition. So once the material is subjected to tensile loading condition, we are going to assess the material at different stages under the heading called as cup and cone fracture. So how we go with the different stages? See, stage A is a standard material or a test specimen which is subjected to the load called as P here. Upon increasing in the load over the same test specimen which is at position A or stage A, there will be reduction in the cross-sectional area or the area of the material at one particular point, which you can observe here in this particular profile. This is the reduction in the area or the cross-sectional area of a specimen which is observed in the stage 2. This is a resultant of application of load. For this specimen, same specimen, upon further increase in the loading condition, we are going to consider the same specimen which is at stage A at stage C now, wherein a small cavity or voids starts generated at the area wherein the necking is being identified. So this reduction in the cross-sectional area is called as necking, and at stage C, the same necking area will be consisting of different number of or more number of small cavities or voids. To the same specimen, once we go with again increase in the loading condition, what happens? These small cavities or voids try to get collectively resultant in the formation of elliptical hole or elliptical cavity or elliptical ring here within the neck region itself. So again here in position D or stage D, we can observe the formation of elliptical cavity or elliptical ring in the necking area. Upon further increase in the load, this cavity gets extended along its axis and result in the point-to-point cavity in the complete necking region which is observed in this stage E here. So it means to say that this same cavity which was in stage D, upon further extension or application of load, has resulted in the extension of cavity in the same necking region, and at the end, upon further increase in the load, there will be fracture which is generated between the in the material which is subjected to same kind of loading condition. Thereby, it results in two separate bodies, one considered to be cup, another considered to be cone. So this is what something called as cup and cone fracture. So this is moderate or cup and cone fracture type of ductile fracture which will be observed in the materials. So this is one of the major question which will be generally repeated in the examination. So this is to be focused very intensively during your studies. Moving on with the next one, that is type 2 or brittle fracture. So what is type 2 or brittle fracture? See, when the material is loaded in case of a ductile fracture, what we have assessed, it is slow propagation of crack. Whereas in case of brittle fracture, the propagation of crack will be very instant. Means to say that similar to the understanding of cup and cone fracture, definitely if there is a fracture being initiated in the material, there will always be generation of cavity, there will always be reduction in the area just like necking here. So as such, but in case of brittle fracture, all these type of initiations for the fracture happens instantly and thereby results in the formation of a material which is subjected to the load called as P into two separate bodies. Here, when the material is brittle in its nature, the fracture results in separation of the body perpendicular to the axis of the loading condition. So you can observe the figure here. So this is a test specimen which is now separated into two parts upon the application of load P here. So here the breakage or the separation of material is perpendicular to the loading condition. So the separation will always lead to two separate bodies which is perpendicular to the direction of loading condition. And the last one is supposed to be the type 3 or shear fracture. In the module 1, almost at the last of the topic, we have studied something called as plastic deformation by slip, plastic deformation by twinning. So here, when there is a plastic deformation which is being observed in slip, that leads to the type of fracture called as shear fracture, which is generally identified in a material of ductile in its nature, that is a material with single crystal ductility in its parameter. So here what happens, similar to the brittle fracture, here in the shear fracture, upon application of load, the material after reaching a particular point gets separated into two pieces or two parts, while the surface in which the fracture results is almost at 45 degree to the vertical reference. Means to say that in case of brittle fracture, the surface of segmentation will be perpendicular to the loading condition, whereas here in the shear fracture, it will always be around 45 degree or inclined to almost 45 degree surface to the type of loading which is being applied. So this is something regarding different types of fracture. I repeat, fracture is defined as the separation of solid body into two or more parts under the action of load. So please keep in mind, separation will always be considered when the material is completely broken into two parts. Now we shall study the second type of failure of materials, that is fatigue. So how do you define fatigue? Fatigue is a behavior of metals under repeated cycle of stresses or strain that results in progressive fracture. Means to say that there are different types of loading conditions that leads to the failure of material. So if there is a continuous amount of load being applied on a particular member till it leads fracture, we have studied it in the behavior of material under fracture. Now here what happens, here we are concentrating on the repetitive or alternative load applied on a member that leads to failure of material over a period of time. That is, if the loading condition of alternative or repeated type of loading conditions is considered for a huge number of cycles till the material fails, then the material is subjected to the behavior called as fatigue. So you can just observe the examples which are quoted here under the behavior of metals that leads to fatigue is, one is deflection of springs. Maybe we can take the example of toys or the spring which is present in the pen. Okay, so alternatively, once we press the spring will be subjected to compression. Once we release, the spring will be subjected to tension, that is, it come back to its original condition. Till the limit wherein the spring can be retained in the elastic limit, the spring tries to come back to its original condition. Else apart, it leads to the fracture and the behavior will be considered as fatigue. Followed by the aircraft springs that are subjected to gust loads. So this is irregular mode of load which is being applied on a member. Okay, so each and every metal or a material, whatever we consider for any practical application, has its own life cycle. Over a period of time, there will be certain amount of deterioration in the surface of the material or the properties, or maybe there will be weak in the atomic bond structure as such. So those are all the things that can be considered for the fracture over a period of time, but the loading condition here goes with the alternative or irregular loading conditions that is considered in the aircraft. Followed by the deformation in the rubber tires. Every time the tire rolls on the ground surface, there will always be wear and tear on the surface of the tire. So at that particular point of time, there will be deformation that leads to the behavior called as fatigue. So these are the few of the examples that can be considered to understand the concept called as behavior of material under fatigue condition. Followed by, we have different types of fatigue loading. First one is completely reversed cycle of stresses. So the best example is, you can observe in this particular figure, assume that this is a thin steel wire and this wire is being applied to a load such that it is bent along its particular profile. So this is the bent profile of the steel wire. When it is bent, the outer profile of the same steel wire will be subjected to tension loading condition, whereas the inner profile of the steel wire will be subjected to compression loading. So here the load application is same, but the behavior of material due to that particular load is differed. That is, outside tension, inside it is compression. So this is one simple example for the repeated cycles or reverse cycles of stresses that can be assumed in the material over a particular period of time. Next, followed by repeated stress cycle. So means to say that, as we considered the example of springs in pen or toys, so that can be considered as here as the second type of fatigue, that is repeated stress cycle. Here, the major difference between the completely reverse cycle and the repeated stress cycle is that the first one will be completely consideration of both the types of loading conditions at each interval, whereas in case of repeated stress cycle, it is only the tension loading conditions that leads to the material to behave in the fatigue pattern. So you will apply the tensile load condition, then you will remove it, come back to its original condition, or over a period of time due to only tension the material fails. The last one is random stress cycle type of behavior wherein the fatigue loading condition. So this is the example what we considered here for the aircraft wings, wherein the application of load will be completely irregular or not normal. So let us explain the same three different types of fatigue loading using these particular diagrams here, which represents the stress versus number of cycles to failure is the consideration of the diagram here. Along the y-axis it is stress, along x-axis it is the number of cycles that leads to failure in the material. So here we consider the mean position or zero condition. That means to say that above the zero line it is the load which is being applied in the tensile condition, and below the zero line that leads to compressive loading condition. Means to say that that has to result in fluctuating or repeated loading condition. Here the load is not steady as we studied in terms of fracture. So you can observe the repeated number of cycles that leads to the variation in stress here. So in the compression there will be a maximum loading condition wherein the stress can be considered, that is sigma max, and in the compression that is sigma minimum here. So the length between the zero value and the sigma max is considered as sigma amplitude, and the distance between sigma max to sigma minimum is called as sigma r, that is sigma range here, and the zero line of coincidence is considered to be sigma mean. So these are the parameters which we generally define to describe which type of loading condition the material is being subjected to. So here along x-axis there is number of cycles being represented over a period of time. Upon consideration of number of cycles, the material leads to failure. So if the material is subjected to alternate loading condition in one cycle, that is, the simple example is this: tensile is applied, compression is also applied in one particular loading condition or behavior. That is the simple example for completely reversed cycle of stresses or simple fatigue behavior. The second one is repeated stress cycle. Here you can observe in the figure the sigma is only tensile here, that is the stress is only due to the tensile loading condition and not due to the compression. So here if you can observe, the entire behavior of material over a period of time, that is over number of cycles, is assumed to be present only in the tensile loading behavior or tensile loading condition. So you can observe the same parameter here. So we have sigma max, sigma minimum, sigma range, sigma amplitude as such. So the only thing to be concentrated here is that the material is subjected to only tensile loading condition, whereas the third one, as the figure itself represents, the stress and number of cycles is not dependent on one particular type of loading condition. It is subjected to any number of parameters which can be considered. Say for example, environmental factor, maybe temperature, maybe the wind speed, etc. If we consider the example of the aircraft wing that is subjected to gust loading condition as such. So here the load is not proper, but over a period of time, when the load is not proper, that is when the random or loading condition is being subjected over the material leads to failure, and hence it is considered to be under random stress cycle under the type of fatigue loading. Now we shall take up the second part of the fatigue loading, that is different mechanisms in fatigue loading. Now let us take up the topic on the mechanisms of fatigue failure. So we have two theories here to represent the mechanism of fatigue failure. The first one being Wood's theory and the next being Orovon's polycrystalline model theory. So let us go with the Wood's theory first. So the Wood's theory always defines based on the formation of slip that is due to the shear stresses acting upon the surfaces of the material. So once if we say there is a slip formation, it is indication that it leads to deformation of material along a particular direction. So if you can just remember the definition of fatigue what we have taken, at the last we have written as progressive fracture. So that is what we are going to now assess here in these two theories. So consider we have four different stages to represent wood theory here. So consider a material which is subjected to shear stress condition. So if this is the normal surface of this specimen which is subjected to shear stress condition, there will be a resultant of formation of slip upon continuation of the shear stress loading condition here. So see, this is a formation of slip over the surface of the specimen which is considered to be under the testing condition. So here what happens when there is, when we alternatively apply the load on either side that leads to shear condition, there will always be movement of slip even in the opposite direction. Means to say that along the direction of loading condition over the specimen, the slip will always try to move in the opposite direction. So you can just observe here, we have identified a formation of slip over a material which is subjected to alternate loading condition, which can be generally defined under shear stress loading phenomenon. So once the slip is formed, thereby upon further increase in the load, to define the term called as progressive fracture in fatigue behavior, we are going with this. There will be different irregularities being identified over the surface of specimen. So this was the slip identified. Now we have one more projection upon the surface of specimen, and this regularity is called as slip band. So we can identify the slip band here which is above the surface of specimen, as well as we have one more slip that is below the normal surface of the specimen. Further increase in the load, this slip band will accumulate or generate more in number, and again it moves in the opposite direction of loading condition. So you can observe here we have multiple number of slip bands here above the surface as well as the below the surface of the specimen. These irregularities which are above the surface is called as extrusion, and the surfaces or the slip bands which are identified below the normal surface of the specimen is considered to be intrusion. This extrusion and intrusions are the irregularities that develop in the material due to the fatigue behavior that leads to the deformation of material over a period of time. So this type of condition justifies the word called as progressive fracture, which we define in the fatigue. Now moving on with the second type of theory, that is Oravan polycrystalline theory. You have to assume that there is a polycrystalline member here which consists of a grain called as A, which is very weak compared to the neighboring grains here. So once we have a weaker grain inside the polycrystalline structure, what happens is that this polycrystalline member will be subjected to opposite loading conditions. So maybe along the right as well as along the left of the visible or the viewer here. So when the load is being applied on either side of this particular polycrystalline member, based on the direction of load, this weaker grain, that is A, tries to yield, means to say that it tries to deform. So when we have alternative loads being applied on either side of the weaker grain, when the load is applied towards right, there will be yielding of weaker grain A towards right, and when it is being made towards left, there will be yielding of weaker grain towards left here. So this right and left moment is directly dependent on the direction of loading condition. What happens when the weaker grain is present in the polycrystalline member? This weaker grain yields very fast than the other grains present in the polycrystalline, means to say that the initiation of crack leads directly from the weaker grain, that is A. So due to which there will be submicroscopic crack initiation between the weaker grain and its neighboring grains. So progressively what happens when the same type of alternate loading conditions is repeated, this submicroscopic crack leads to a crack, and that leads to a cavity forming the or resulting in the fracture of a material over a period of time. So here both the theory represents the failure of material when the material is subjected to alternative loading condition repeatedly over a period of time. So that leads to progressive fracture, that in turn or in general we can accumulate the entire process considered to be under the fatigue behavior. Now we shall discuss the SN testing method or fatigue testing method with SN diagram. So we have a specific standard method RR Morse test to define the fatigue behavior of a material, wherein which we are going to define the stress versus number of cycle, that is SN diagram, to represent the behavior of material using the when the material is subjected to fatigue loading conditions. So we are going to take up that topic now. Now we shall study the concept of fatigue testing. So basically RR Morse fatigue testing is considered in order to analyze or assess the behavior of material subjected to fatigue loading condition. So here the fatigue test rig of RR Morse type consists of different components here. So this will be a specimen which is housed between the two bending housing platform, wherein the bend house platform are connected to the additional weight here. Meanwhile, the specimen with the bending housing platform will be fixed such that its axis of rotation will be same as the axis of rotation identified in the high-speed motor. So followed by flexible coupling that tries to retain the position of the specimen or retain the axis of rotation of specimen, and followed by at the end the revolution counter, which accumulates or measures the RPM at which the motor is being considered. So here what happens during the operation, so the specimen will be fixed between the two bending housing condition, it will be subjected to additional weight W here. So once we switch on the high speed motor, the specimen will be subjected to rotation along a particular direction. When it starts rotating along a particular direction, once the weight is added to the member, or once his weight is added to the bending housing platform here, what happens is that you can observe the specimen condition here. The uppermost fibers of the material and the bottommost fibers of material will be subjected to compression and tensile loading condition respectively. So here this is the uppermost fiber part of material and this is the bottommost here. So bottommost is subjected to tensile loading condition and uppermost is subjected to compressive loading condition. So it is as simple as, like, bending a wire illustration what we took in the explanation during the fatigue. So here what happens, this specimen will be continuously rotating. So means to say that at any instant of time, if you observe the material, the uppermost fibers of the material at one particular position will always become the bottommost fiber of the material at any other instant. That is, the material will be subjected to loading condition. Hence, it is completely possible that the fiber will be subjected to compression and tension alternatively during the rotation. So here what happens, this many number of rotations is not fixed for a specimen to fail at the beginning, whereas once we just start providing the supply from the motor to rotate the specimen, upon additional adding of weight here, at particular point of time the specimen leads to failure, and the failure of material is thereby encountered with the number of cycles or the RPM which is being generated or accounted in the revolution counter. So using this, we are going to plot a diagram called as SN diagram. So I'll repeat here, the specimen will be subjected to rotation using the high speed motor. Once the subjected specimen is rotated along a particular direction, along with the additional of weight, it is added at the bottom here, the uppermost and bottommost fibers of the material will be subjected to compressive and tensile, and it is fluctuating or alternatively going to same because the specimen is continuously rotated due to the high speed motor, and the number of cycles that leads to the failure of material will be accountable or taken from the revolution counter. So here what we do is, we are going to plot the SN diagram based on the convenience or based on the description in which the material is to be identified or it is to be analyzed. So here you can refer the stress along y-axis and number of cycles along x-axis. The stress can be sigma A or sigma max or sigma minimum, as we just studied in conditioning or understanding the principle of different types of fatigue loading. So whichever stress is applicable for that particular material, to define that particular parameter, we are going to plot that stress, and along x-axis it is the number of cycles that leads to failure. So usually along x-axis the number of cycles n will be taken in the logarithmic scale. So when we plot this stress versus the number of cycles in log scale, so you are going to get multiple number of points for a particular material when we define sigma A, sigma max and sigma minimum as per the condition. So what we do, once we plot all those comparison between S and N, we are going to just draw a line and we are going to assess the behavior of material or the behavior of material due to fatigue loading condition. So next we are going to study the topic called as fatigue properties. The last topic under fatigue is fatigue properties. So we have 5 different fatigue properties to be studied in this particular module. The first one is fatigue life. So it is only the definition part what we are focusing on in this particular content. So fatigue life is the total number of cycles required to bring about final fracture in a specimen at given stress. So we know that a material, if it is subjected to alternative or fluctuating load condition over a period of time, that is nothing but the fatigue loading condition. So we have 3 different types as well in the fatigue loading. If the number of cycles that are required to bring the exact failure of a material is targeted, then that becomes the fatigue life of the material. Followed by the next, that is extraction of the first definition itself, that is fatigue life for P% survival, means to say that it is the fatigue life for P percentage of the samples which are being tested to be survived. So the definition goes like this. It is the fatigue life for which P percentage of population of sample tested have longer life than the rest, means to say that as the name itself suggests, survival. So it is the life which is defined for P percentage. Say for example, if it is N, 90 is represented, so 90 becomes the survival percentage for P, that is 90 is the P value which is being accounted. So that means to say that these amount of P specimen, that is P% of specimen, have better life than the remaining specimens in the condition. Moving on with the median fatigue life. So it is, as the name itself suggests, it is median. It is 50% of the fatigue strength that leads to failure as well as survival in the material. So it is the fatigue life for which 50% of the sample fail and other 50% survive at the given or a particular stress. So this is nothing but the 3 definitions related to fatigue life. Moving on with the fourth one, the important one, that is fatigue strength. So we define fatigue strength as the stress at which a material can withstand repeatedly n number of cycles before failure. Before the material failures, the alternative or fluctuating loading condition as per the fatigue behavior, what is the maximum stress wherein which the material can withstand for a fatigue type of loading condition, that is considered as fatigue strength here. And the last one, fatigue limit. So it is the stress below which a material will not fail for any number of cycles, means to say that for a fatigue loading condition, the fatigue limit is a limit below which there will be no failure of material taking place. Above that limit, if the loading condition is exceeded, that results in the final fracture of material. So this is the session on fracture and fatigue for today's session. Thank you.